Okay, so we are in Chapter 7 of the second edition of Statistical Rethinking, and we are looking at questions 7M5 and 7M6, and we're going to tackle these in one go here because they're very similar. So here's 7M5. So provide an informal explanation of why informative priors reduce overfitting. And then 7M6 is provide an informal explanation of why overly informative priors result in underfitting. Okay. And so you can read my answer here, and I'll make reference to it. But we saw everything that we needed to see in order to answer these two questions in our answer to 7M4. Okay, so I'm gonna scroll back up there to that here in just a second. So, but first, let me kind of define how I think about overfitting. So I tend to think of overfitting as occurring when models mistake noise in the data for signal. Okay, and so the consequence of that is that when we go to deploy that model on unforeseen data, or I'm sorry, not unforeseen, but unseen data on which the model has not been trained, because the model is assuming that there should be signal there, or a type of signal which is not there. Right? That signal was actually noise from the previous training data. Then it will struggle to make good predictions or inferences on the new data. Okay. So we see that priors are kind of telling our model which values which parameter values, possible parameter values, should seriously be entertained as being possibly accurate values for those parameters. Okay. So when we went when we did the exercise in the previous problem, we fit a diffuse prior model as well as a concentrated prior model, okay, and so to a regression, okay, where the y variable was a function of x, and it was about twice x, okay, and so in the diffuse model, okay, we set the prior, the standard deviation of the beta term to 10. So this was so our prior considered many values for beta x, and in the concentrated prior we set the standard deviation for beta x to 1. So this is this prior is considering a much narrower band, or seriously considering a much narrower band of possible values for beta x. Okay. Now the appropriate value, or the correct value according to the data, should have been about 2, and that's going to change with the fact that we randomly generated this data. So whether or not the data actually came out to where 2 was the best estimate or not, that has to do with the random sampling. But anyway, when we look at the posterior distribution for our values, we see a couple of things. One, so here's the summary for the concentrated model, and the top one is the summary for the diffuse prior model. Okay, we see one, that the concentrated prior is much closer to the actual value of 2 than it is for the diffuse model. Okay, and again, this is because the concentrated prior didn't allow us to seriously consider values much further away from 2, right? That's what we set it at. Okay, and also notice that the credibility intervals here are narrower, okay, for the concentrated prior than for the diffuse prior. And again, this is because the concentrated prior is seriously considering fewer possible values. Okay, so we see then that the concentrated prior filtered out some of the noise that is being picked up in the more diffuse prior model. Okay, and so we would call that we would call the noise that is being picked up by the beta x, right? So the deviation from 2 to 2.32 here, there's noise in that interval right there, okay, between 2 and 0.32, or I mean, that's not a rigorous definition of what the noise is, but it's mistaking some of that noise as signal, right? Okay, and our concentrated prior is doing a much better job of filtering out some of that noise. All right, so that's good. So this explains. Okay, so this explains why an informative prior reduces the overfitting, because it's filtering out the noise that would otherwise be mistaken as signal. Okay, but now the next question is provide an informal explanation as to why overly informative priors result in underfitting. Okay, so we also saw something for this. So in the example that we just looked at, we cheated a little bit, okay? We cheated because here, so the value for which, the value of the beta x term is 2, and we centered our priors on 2, okay? And that's kind of cheating, maybe. So we could be working in a system where we have a pretty good estimate of what beta x should be, just given other data, right, from previous data, right? But it's possible that we don't have that at all, right? That given our state of information, what is actually better is we assume that beta x is 0, okay? Even though the actual value for beta x should be 2, but given our prior state of knowledge, we might put it at 0, okay? Well, now think about what's happening. Now, for the concentrated prior, the beta x term is centered quite a ways away from the actual value, and it's considering a narrow band, right? So it's considering, from like -2 to 2, but by the time you get out to considering 2, it's assigning pretty low probability to that value, right? Whereas even though the diffuse prior is also centered pretty far away, but because it is considering many more potential values, or seriously considering many more potential values, 2 is well within the values that the diffuse prior is going to seriously consider. Okay, and now what we see is an inversion of what we saw previously. Now the beta x term for the diffuse model is closer to the actual value than for the concentrated model. We also see that the credibility intervals are still wider for the first model, but that is okay here. That's what we would expect, because again, it was considering a broader range of potential values, and in this case, that's actually good, because that allowed us to actually begin to hone in on, or more rapidly hone in on, an accurate value for the beta x term. Okay. I think that is it. Like I said, you may want to read through my answer on the Colab sheet and just kind of place all of that in context for yourselves, but that is it for this.